Hello everyone, welcome to this video tutorial on finite element analysis, a practical approach using ANSYS. So myself, I am Shankar, Assistant Professor Mechanical from Tyagaraja College of Engineering, Madurai. So before getting into solving a problem using ANSYS, let us initially understand what are all the steps involved while solving any problem using any FEA softwares. So these are basically the steps that you have to follow while solving any problems. So it can be categorized into three major steps. What we call it as pre-processing, solution or processing, and post-processing. The majority of our work while solving using any FEA software lies in pre-processing. So it can be categorized into defining the problem, whether it may be thermal, structural, dynamic. You have to identify your problem, then select the proper element, then define your material properties and section properties if necessary, then model your problem, then you do an important part called as meshing, and you then decide your boundary condition and you give the loads, you apply the fixtures, supports, etc. And this is where your work starts. And the solution, it is the part of the computer, it is a part of the FEA software to solve your problem and give you the result. And finally, after the results have been arrived, you have to check your results and you have to observe, conclude from your analysis, provide suggestion, and you can prepare your own report. Right. Now, let us get into the list of exercises that we are going to see one by one. So in this video tutorial, we'll start with our first exercise on analysis of deformation and direct stress in a stepped shaft. So this is going to be a series of videos which is going to combine, in which we'll be seeing each one of these upcoming exercises individually. So today's exercise, it is going to be on analysis of deformation and direct stress in a stepped shaft. So this is cycle 1, then you have cycle 2 thermal exercises, and cycle 3 dynamic and coupled analysis. So as I said, we'll be seeing each one of these exercises in the upcoming video tutorial. Now let us get into our first exercise on analysis of deformation and direct stress in a stepped shaft. So this is going to be my first exercise actually. This is my problem. This is a little bit complicated problem. I have included all the different variations that a problem can meet, so that if you understand solving this single problem, then you may be able to solve any kind of stepped shaft problem. So what I have here is that I have 1, 2, 3, 4 and 5 sections, and all these sections are made up of different materials. So first we have a steel, then you have aluminum, and this is titanium, this is copper, and finally brass. And also the cross sections are different, so you can find a reduced diameter, here you find an enlarged diameter. This section, it is actually a hollow diameter, maybe you can't see here, but it is actually hollow diameter. And this is again a solid section, this is a tapered circular section. You have variation in material, you have variation in cross section. So this is a little bit complicated problem. So now the second step. So in order to understand this problem clearly, this is my second stage. So this is my dimensional values and the loading conditions. So I have given the diameters value and I have 3 loads in this. One end of this shaft is fixed, and I have 3 loads, P1 5 kN here, P2 10 kN acting here, and P3 15 kN acting at this end. And the corresponding materials have been detailed in this section. So as you said, this intermediate section, it is a hollow section. So this is a solid circular, this is one solid circular, and this is also a solid circular of varying radius. This is a tapered section, and this center portion is a hollow section. Maybe this is not a real life problem. You can't find all these different materials attached with each other in a single real life problem. This is just for the understanding of different complications in a single problem using our software ANSYS. So okay. So in order to solve this problem, while solving using any FEA software, not only ANSYS, which I'm going to teach you, but using any FEA software, first of all, try to simplify the problem. So as you know that every problem in nature is three-dimensional, but you don't need to solve it the way as it is. You can simplify the problem to a two-dimensional problem or even a one-dimensional problem. So as you simplify the problem, the solutions that you get by simplification will actually meet with your analytical solution very closely. The error is being reduced very much. Okay. We'll see the advantages of simplification in a later part. Now, I'm going to simplify my given problem. So this is my problem, a three-dimensional structure. I'm going to simplify it like this. I'm going to just simplify this three-dimension to a one-dimensional problem. I'm going to draw lines. So I'll take this part. So this first part is my first line, and from here to here I have my second line. Then I have my third line. Then this hollow section represents my fourth, and this red color copper region represents my fifth, and finally this tapered region has been drawn as a single line. Okay, that would be my sixth line. So this is how I convert this 3D problem to a one-dimensional problem, and for this each one-dimensional line I will define the corresponding material and the corresponding cross section, so that it will assume that it is a three-dimensional problem, right? So this is my first step. So it completes here the problem definition. So problem definition is that you must know all the data relevant to your problem, all the material data, all the geometrical data, and find whether you can simplify a problem into a two-dimensional or one-dimensional one. So this is where step 1 gets completed. Then step 2, you have element selection. So as the problem has been converted to 1D, we will use one-dimensional elements. Right? The 1D elements present in ANSYS. So as you know that I'm going to use ANSYS for solving this problem, I'll teach the elements present in ANSYS. So the 1D elements present in ANSYS are link element and beam element. For this problem, we'll be using the beam element. There are some categories in beam element. We'll be using the beam 2-node 188 element in ANSYS for this exercise. This 188 is a reference number for the ANSYS, and this 2-node means that the beam element, which looks like this, it is going to have 2 nodes at the either end of the element. So this is called as a beam 2-node element. Some definition on beam 188. This beam 2-node 188 element, it has a 6 or 7 degrees of freedom at each node, and these includes 3 translations and 3 rotations. A 7th degree is an optional one. It is for warping. This beam element is well suited for linear, large rotation, or large strain, or non-linear applications too. It is also suitable for analyzing slender to moderately stubby thick beams or bar structure. So in our case, we are going to analyze this beam element for a bar structure. This element is based on Timchenko beam theory. So these are some of the basics on what this beam element will be. You may find this useful while studying theoretical part of finite element analysis. So this is where your second step ends. The third step is material property and section properties. As you know that we have around 5 different materials in our problem. This is a material chart that I have, and I can find almost 8 materials here. Out of these 8 materials, I am going to use 5 materials for this problem, and the corresponding Young's modulus, shear modulus, and Poisson's ratio are given, which I can take it from this table. And as you know that I have converted the problem from 3D to 1D. Definitely, I need to give the sectional properties in order for software to understand how it is going to be in 3-dimensional in nature. So I have to give the circular sections with solid, taper, or hollow regions, and we have the corresponding diameters as shown in the figure. So this is just a definition stage, nothing much detail in this step. So now we can get to the fourth step, which is basically a modeling stage. So modeling, we can convert this problem to this one-dimensional problem. So in order to draw this model, all these consists of individual lines. In order to draw lines, I need points. So 2 points. For drawing a single line, I need 2 points. In ANSYS, the points are called as key points. So for drawing the 6 lines, I'll be having 7 key points, and the corresponding coordinate values are given here. With the help of this length, I have calculated this coordinate value. So here this is 50 mm length, so 50, 0, 0. Then you add with 75, it gets 125. This 125, when you add with 100, you get 225. Then with 150, you have 375. Then with 80, you have 455. With 200, you have 655. So I'll take this to be the origin point, which is 0, 0, 0, and the entire length has been converted to the corresponding coordinate values, which will be helpful in drawing these key points. After you draw the key point, then you use line command to join these key points in order to create this geometry. Then so modeling, there's a thing, there's a rule for modeling. So the thing is that rules for keeping key points. So here I have 7 key points in my problem. So I have 1, 2, 3, 4, 5, 6, 7. So there is some rule based on which the key points have to be kept. So that rule I have given here. So the rules for keeping key points. So the key points has to be present at the both end of the problem. That is a necessary one. And the key point can be kept when there is a change in cross section at a particular area. And also the key point has to be kept when there is a change in material. Also the key point has to be kept at locations where boundary conditions like a fixed roller support, hinged support are present. Also key point has to be present where there is a loading is present. So in our problem we can find it here. I have followed all these rules while modeling. So here I have, this is the end of a problem, and also there is a support, so I have kept a key point. As you move along, the cross section is same, the material is same, and here I have a load. So according to our rule, we have to keep a key point here. Then as I move further, you can find here I have a change in cross section, I have a change in material at the same point, so I have to keep a key point here. Then as I move along, the section and material is same, and at this location I can find a change in material, change in cross section, or also a load is present, and all these are present at the same location. So I'll have a single key point to represent all these. You don't need to have different key points to represent all these individual things. If you have something that is coinciding at a particular location, you can have a single key point. Then as I move along, here you can find a change in cross section and material, I have a key point. Then as I move along, again a change in cross section and material, I have key point. And finally have a load, and also this is the end of the problem, so I will have a key point. So this is how I have kept the key points. So this is one important thing while modeling. Okay. After the completion of modeling, then there is the important step that comes is meshing. There are 3 steps in meshing. One is mesh attributes, dividing into segments, and mesh. So what mesh attributes mean is that telling ANSYS that each line has this section and this material. So we know that by looking at this problem, we will be able to understand that, okay, so this line is steel and it has a cross section of 30 mm. And by looking at this line, I'll be able to understand that, okay, it is made up of aluminum and 60 mm. And by looking at this line, I'll be able to understand that it is a copper and having a geometrical diameter of 50. But how does ANSYS know that this line has this corresponding material and this diameter? Then you have to tell ANSYS that this line is going to have a particular material and a particular cross section. That is where mesh attributes come into play. Similarly, after finishing this mesh attributes, then you have to divide into segments. So the entire point of finite element analysis is to divide a large problem into a smaller number of individual pieces, then solve for one piece, each individual piece, then assemble the total thing and solve it. So this is the basics behind FEA. So that is what we are going to do here. Telling ANSYS on how many segments that each line is to be split. And after you divide these segments, you have to join them in order to get an assembled problem. So converting the ordinary problem into an FEA problem, which means you are forming the elements and nodes. Before this meshing, you will be only having points and lines. After completion of this meshing, you will have elements and nodes. So this is the stage where meshing comes into play. Then after meshing, you encounter the last final step of our pre-processing stage, which is boundary conditions. So what are the boundaries? So here I have a fixed region, which is boundary condition, which I have to apply at this point. Here I have the second boundary condition, which is a load, which I have to apply at this key point. I have another load which I have to apply at this key point, and another load which I have to apply at this key point. So I have 4 boundary conditions, and this is the final step in pre-processing. So conditions in boundary. So boundary conditions are such a way that it has to be a fixed. So in fixed, which means the displacements are 0. So all the 3 translations and 3 rotations, which means the 6 degree of freedom is arrested completely, which means the displacement all the 6 degree of freedom is 0. And force or moment, force can be applied in any direction, f of x, y, z, and similarly moment can also be applied at x, y, and z. The sign convention is as usual. The right side x is positive, left side x is negative, upward y is positive, and downward y is negative. So this pretty much completes our work in solving a problem using ANSYS. And after this stage, the computer takes over and solves the problem for you. So this is where the manual work gets ends. Now, how to solve in ANSYS? As we have seen this problem, the various steps in each stages. Now we'll look at ANSYS and we'll see how to solve this problem in ANSYS. So in order to open ANSYS, you can go to start menu and you can find an ANSYS menu, and under that you'll find a menu called as mechanical APDL. In ANSYS there are 3 design work environments. In the latest version, of course I am using 19.0, we have 3 design environments. One is called as this APDL, the other one is called as workbench, and the third one is called as AIM. Right? But this APDL is one of the oldest design environment that is present in ANSYS. So ANSYS is a very old software, FEM software, and it dates really back to 1990s. Okay, still then we are using this ANSYS for lots and lots of analysis. This APDL, which means ANSYS Parametric Design Language, it is one of the oldest design environment which is present in ANSYS, and it is still now. So all the exercises will be solving only using this mechanical APDL. So once you click this, you will find a window like this. So this is my ANSYS APDL window. You can find a black screen with some menu bars at the right and some menu bars at the left, and you have some options at the top. So this is the environment that we are going to use in order to solve our step to bar problem. Okay. So the first thing that you have to do is that you have to set the preference that which type of problem am I going to solve, whether it is a structural or a thermal or a fluid problem, magnetic. So as you set this preference, the corresponding options below this would only occur corresponding to the preference that you have selected. So as I have selected structural, the options related to thermal or fluid or magnetic will not appear in this sub-menus that I am going to follow. Right? In ANSYS, we follow an approach of top to bottom approach, which means the options that you can see from the top to bottom, I'll be moving one by one downwards. Okay? And these are some of the menu bars that you can find at the top, which I'll discuss while solving the problem. Right? So next, so the first step is defining the problem that we have pretty much done here actually. This is the definition of the problem, which I have already completed. So after the problem definition, the second step is element selection. So that you are going to do. So click on this element type, click add, edit or delete. So a window opens, click on add. So you can find beam. Under the beam, you will find two nodes. So you can find lots of elements present, each one to peculiar problems. Right? But as for us now, we'll use this beam and particularly this 2 node 188, and I'll click OK. So you can find beam 188 being added. Here this 188 is the reference number for ANSYS. This one, it is the reference number for us, for the user to keep in mind that 1 means that I am using beam 188 element. You can similarly add as much elements as you want here. But here I am going to model the entire problem using beam 188. So I'll add only one element. I'll close this. So the element stage has been completed. The third step is defining material properties and section properties. So click on material properties, click on material models. So the material model number has been added as you can find here. Okay, I'll just expand it for a moment. Okay, material model number 1. So this is the first material that you are going to add. So as we have 5 different materials: steel, aluminum, titanium, copper, and brass. I'll add 5 different materials. So all these materials are elastic and isotropic in nature. I will provide the material properties of Young's modulus and Poisson's ratio for all these 5 materials, which I can find here. Okay. This is the step. Okay, so steel. First is series. I will come in order. In series, first one is steel, second one is aluminum, titanium, copper, and brass. So just keep this in mind. So we'll come back in a moment. So first is steel. For a steel, I have an Young's modulus of 207 gigapascal and the corresponding Poisson's ratio is 0.3. One of the important things to note in ANSYS is that ANSYS APDL does not keep an account of the unit system. So the unit system that has to be kept in mind only by the user. So either if you are going to give the length unit in mm, you have to follow that mm throughout the problem. If you are going to follow the force unit as Newton, then throughout the problem you have to keep the force unit as Newton, which the user has to keep in mind. The ANSYS APDL does not take into account of any unit systems. Okay, right. So I'll keep the force unit in Newton, and then I'll keep the length unit in mm. Okay, so this is first material model number 1, which is added by default. I'll click on structural, I'll click on linear, elastic, elastic and isotropic. So my material property is given as 207 gigapascal. So convert this gigapascal into megapascal, which is Newton per mm square. I have to add 10 to the power 3, which means 207 into 10 to the power 3 Newton per mm square or megapascal. So whatever it is. So 207. In ANSYS, for feeding into 10 to the power, we'll use a sign called as E. The E means into 10 to the power of. So 207 E3 means 207 into 10 to the power 3. And the Poisson's ratio value, which is 0.3. So as I have added the first material, I'll click on OK. Then add the second material. So in order to add a second material, go for material, new models. Let the ID to be default. Okay. Then I'll click on isotropic. So I'll add the second material. So the second material is aluminum. For aluminum, I have 69 gigapascal and 0.33 as my Poisson's ratio. So 69 gigapascal, which means 69 E3 megapascal or Newton per mm square, and 0.33 Poisson's ratio, which has no unit, as we know. Click on OK. Then I'll add my third material, which is titanium. And for titanium, I have my Young's modulus to be 107 gigapascal and the corresponding Poisson's ratio 0.34, which I'll give it here. So isotropic 107 E3, which is in Newton per mm square, and 0.34 Poisson's ratio. Okay. And the next material is copper. So I'll add a new material, new model. I'll click on OK, and I'll click on isotropic. And for copper, the corresponding Young's modulus is 110 gigapascal and 0.34 Poisson's ratio. So I'll give it as 110 gigapascal, which is E3 megapascals, and 0.34. Okay. And the final fifth material that is present in my model is brass, which is 97 gigapascal and 0.34 Poisson's ratio. So the final fifth material with the ID 5, it has a it's an isotropic material. So which is I'll just give you my 97. So 97 E3 megapascal and 0. I think it is 0.34. Okay, 0.34. So please be careful while giving the unit. So ANSYS is a black box software, which means whatever the input you give, it will process it and it will give you the output. In case if I give the Poisson's ratio to be 34, it will do the analysis and it will give you the result, some erroneous results. But as you know that there is no material in the world that has been invented till now which has a Poisson's ratio of 34. There is not a single material in the world. Poisson's ratio range has to be within 0.2 to 0.45. So there is no material beyond this point which has a Poisson's ratio greater than 0.45 or less than 0.2. So please be careful when giving your input in ANSYS. So as I have added 5 materials, all these numbers corresponds to this material which you have to keep in your mind. So 1 represents steel, 2 aluminum, 3 titanium, 4 is copper, and 5 is brass, which I will keep in mind. So once I have defined the material, then the next important thing is that I have to define the section properties. So section properties, I will be giving the corresponding diameters. So I have here, I have to add the first section here. So 30 mm, 60 mm solid circular. Again, I have a hollow circular region here. Again, I have a solid circular region, and I have a tapered region here. I have to add all these sections in order for ANSYS to compute. So get to sections, open beam, click on common sections. So we have a dialog box open right here. So let me name the first section as, so my first section is a solid circular cross section with a diameter 30. So let me give a name as SD30, which means solid diameter 30, and the subtype, we have a different section here, section configurations that are pre-default installed in ANSYS. And for my problem I am going to use solid circular, and let these options be by default. And radius, here it is diameter 30, so I have to give a radius of 15. I leave this N and T as blank, right? I'll tell you what it means in a later stage. Okay, click on OK. So the first section has been added. The second section is again a solid circular diameter of 60 mm. So again go for common section. You can find the first data already present. In order to add a new one, change this ID to 2. Now give the name. It is again a solid circular section of diameter 60 mm. So I can find the second section, a solid circular of diameter 60, and so I'll change the subtype to circular, and I'll put it as 30 here, and I'll click on OK. Then the third one is, it is a hollow circular section of outer diameter 60, inner diameter 40. So again I'll go to common section, have the first ID present here. Then if you give 2, you can find your second data present. Then I'll change this to 3 in order to add a new material. So the third one is a hollow circular section of diameter 60 outer diameter and 40 inner diameter. So I'll give a name of HD 6040, and I'll select the corresponding hollow circular diameter with RI, which means the inner radius is 20 and the outer radius is 30, right? And I'll click on OK, and I'll add my next material, which is again a solid circular section of diameter 50. So I'm going to add my fourth section, which is a solid circular diameter of 50. So I'll give this SD50. I'll select a solid circular. I'll give a radius of 25 mm, and I'll click on OK. And finally, I have this taper region. So in order to add this taper region, before adding this taper region, I'll add one more section of 20. I'll add a solid circular section of 20. I've already added the solid circular section of 50. I'll add another one solid circular section of 20. So again we'll go for common section. I'll give a section ID of 5. Then I'll name it as solid circular section of diameter 20. I'll change the subtype to solid circular, and I'll give a radius of 10. Okay, I'll click on OK. So now I have added all the section except this taper section. Instead of adding this taper section, I have added a solid circular section of 20 mm cross section. Now I have, in the left hand side I have a solid section of 50 mm cross section. The right hand side I have a solid section of 20 mm cross section. So if I join these two, then I will get a taper section. So that is what I am going to do. Here you can find a section called as taper section, and using by XYZ location. So let the section ID be 6. Let the name be taper section of diameter 50 20. So TD means taper section with diameter, one side is 50, the other side is 20. So the beginning section ID is going to be SD50. The ending section ID is SD20. So the beginning section ID is this one, and the ending section ID is this one. And it starts from exactly at 455 and ends at 655, 0, 0. So that is what I am going to give here, which is 455, 0, 0. And the ending section ID, ending section location is 655, 0, 0. And I click on OK. So the third step gets completed. Adding material properties and section properties gets completed. Next, you are going to do the fourth step, which is modeling the problem. Okay. So for modeling, click on modeling, click on create and key points. So I'm going to add individual key points from 1, 2, 3, 4, 5, 6 and 7. All these 7 key points I'm going to add one by one. Okay. So let me add it. So in key points, click on inactive CS, which means inactive coordinate system. Click on that. So let the first point number be 1 and its corresponding coordinates are 0, 0, 0. I'll click on OK. Then I'll click on inactive CS. Now the second section is 50, 0, 0 is the second coordinate. So I'll add 50. But in this case, you should not forget to change the key point number to 2. If you forgot that, then the first key point 1 will get overwritten to 50, 0, 0. That is one important thing that you have to keep in mind. Click on OK. So you can find 1 already created here, but you can't see visible here. But you can find the 2 clearly visible here. Similarly, go on adding like this. So another next is 125, 0, 0. I'll change this to 125, and don't forget to change the key point number to 3 and click OK. So the third is added, and the fourth one you can find it here as 225, 0, 0. Change this 125 to 225 and change this key point number 3 to 4 and click on OK. Fourth is added. Similarly, fifth one 375, 0, 0. So in active CS, change this 225 to 375. It's not on 375. Okay, and change the key point number to 5 and click on OK. Then again, after 375, I have to add the sixth key point at 455. So change it to 6. Then give the key point number to 455 and click on OK. And again, the last key point 7, which is at a location of 655, 0, 0. Once I have added all these points, the next step is to join them using lines. In order to do that, go for lines, click straight line, then click the first point, click the second point. Right? A dialog box like this means that you have to select something on screen. Okay, so I have a picking pointer upwards arrow mark, which means that you have to select something. So I'll select the second point, I'll select the third point, third to fourth, fourth to fifth, fifth to sixth, and sixth to seventh. I have joined all these lines using the line command. So once this is the stage where modeling gets completed, so modeling is over. So after modeling, you have to divide this section into individual meshes. So that is meshing stage. You have to divide the entire problem into different subsystems, subsegments. Right? In meshing, there are 3 things you have to do. The first is mesh attributes, which means telling ANSYS that each line has this material and this section. So in order to do that, expand this meshing by clicking on it. And the first option, you have mesh attributes. As I told you, ANSYS follows a top to bottom approach. So you can find that each and everything that I have done is that I'll click this one, then I have come to this one, this one, this one, and here I am a meshing. So you don't need to skip anything. You can come one by one. Right? Of course, there are certain things you need not use. Like in this case, I have not used real constants because real constants are something that is specific to some problems. Not all problems you don't need to use this real constants, but pretty much you follow the top to bottom menu system. Okay. In this, click on mesh attributes, and in mesh attributes, so as I have drawn line here, click on picked lines. So I'll select this. So 1 to 2 and 2 to 3 in this diagram you can find here. Okay. So this 1 to 2 and 2 to 3, these both the lines have the same cross section and the same material. The reason I have split it into 2 lines is that I have an individual load at the center. That is the only thing. But this line 1 and line 2, they pretty much have the same material and same cross section. So I'll select line 1 and line 2 and click on OK. So this material number is 1, which corresponds to steel, and there are no real constants, and all the lines are going to be only a single element of beam 188, and element section, it is first section, which is solid circular diameter of 30, and I'll click on OK. Then I'll pick the line, then I'll select the line 3 to 4. So the line 3 to 4, that is the third line, corresponds to aluminum and solid circular section of diameter 60. So I'll select the third line, I'll click on OK. Now I have to change the material to 2, which corresponds to aluminum, and I have to change the cross section to solid circular of diameter 60. I'll click on OK. Similarly, I'll go for this fourth line, and this fourth line corresponds to titanium and hollow circular section. So I'll click on OK. Then I'll click the third material, which corresponds to 3, corresponds to titanium, which I have to keep in mind while defining the material property. Okay. And I'll select the hollow circular section of 60, 40 and click on OK. Then the final 5th to 6th line, which corresponds to copper. 5 to 6 corresponds to copper and solid circular diameter of 50. So I'll click on OK, and which is the fourth material, which is copper, and here the fourth section, which is solid circular diameter 50, and I'll click on OK. And the final line, which is 6 to 7, it is brass and it is a tapered cross section. Keep in mind, okay. I'll select the final section, final line. I'll click on OK, and here you can find the final material 5, which is brass, and so instead of selecting SD20, you have to select taper section 50-20. Don't select this SD20, which means it is a constant cross section of diameter 20. That is not, that is the wrong case. Here you have to select this taper section that you have already added, TD 50-20. Select this and click on OK. Now we have told ANSYS that each line corresponds to this material and this cross section. So the step 1 in meshing has been completed. Mesh attributes has been completed. The second is dividing into segments. For this, I'll use a command called as, I'll close this. For this, I'll use a command called as size controls. Right? I'll click on that. I'll click on manual size. As I have lines, I'll click on lines and I'll select pick the lines. I'll select all individual lines, all these 7 lines. So, 1, 2, 3, 4, 5, 6. I have 6 lines. I'll select all these 6 lines. I'll click on OK. And here you have some options. Here you are going to divide each and every line segment into a particular number of elements. This is decided by the user. Keep the element to 5 or keep the element to 10, 15, 20, 25 or 50 or 100 or 1000, 1500. It is purely up to the user. There is a particular stage where after a particular number of elements, the solution will always be a constant one, and that particular element is called as the finite. In finite element analysis, the word finite means the number of elements at which the solution that you get matches almost closer with or exactly with the analytical solution. That is where finite comes into play. This can be done only using trial and error methodology. Give 5 elements, then check your results, then go for 6 elements, check it, 7, 8, 9, keep on increasing an element, and at some particular point you will get your final solution, which will exactly or which will match very much closer to your analytical solution. So that particular point is called as mesh convergence. Beyond that point whatsoever, if you increase the element, if you increase the number of elements, the results is not going to change that much. Now for this problem, let me give the number of elements to be 50, which means I am going to divide all this each and every line into 50 segments. As I have 6 lines and I have divided all the 6 lines into 50, so 6 into 50 you have 300 elements. So the entire problem I have divided into 300 elements. So once the size control is complete, don't think that I have meshing is finished, right? So this is not the stage where meshing is finished. So this is the stage where you can find we have just divided it into individual elements. Now we have to join all these elements to form elements and nodes, right? So you can find here it is still only points. It has not converted to elements. In order to convert it into element, click on mesh, click on lines and select all the individual lines. You can find count is 6 and maximum is 6, which means I have selected all the elements and I have clicked on OK. Once I click on OK, you can find the elements being generated. You can find a very single line that is being formed. It doesn't mean that only one element has been created. There is multiple elements that is being created, but it is just showing in a single color. In order to view that multiple elements, whether it has created or not, go for plot control, click on numbering, and in this element or attribute numbering, you have no numbering. Now change that to element numbers and click on OK. You can find a series of some confusions going on there. I'll just zoom a bit, which for that you have to roll your mouse button inwards so you can find the numbers. So these are the element numbers. You can find a colored value. So this is element, this is element, this is element, this is element. So 194, 85, 86 and 192, it goes on as, and it ends here. So I'll just zoom over here. For that, these are the view bar. So I can change the view using all these things. The default view is in front view actually. Front view is the default view that you are seeing. You can change the view. Now we're going to zoom to a particular location. So I'll use the zoom model and I'll just draw a box here. I'll click on drag and box is drawn. So as you can see, so we have divided each line into 50 segments and totally we have 6 lines. So 6 into 50, I'll have 300 elements. So this is what it is. So don't think that once you have completed this, I'll switch off this numbering now, okay, because it is a little bit chaos in here. Okay. Don't think that there is a single color, only one element is created. No, means the colors has been hidden, but the elements, number of elements, as you have divided, as you have defined in size control, it has already been created. Okay, so this is where you convert the ordinary problem into a FEA problem. So our last step, it is going to be giving the boundary conditions. There are 4 boundary conditions in my problem, 1, 2, 3 and 4. So I am going to define each and every one of them individually. So in order to do that, I'll come to loads. The in-between options, checking control, numbering control, ANSYS model, coupling and multi-field setup, it is peculiar to some specific problems. Not all the problems need all these steps. So I'll leave all these steps, skip all these steps, and I'll come to loads. And in loads, I'll define loads, and then for define loads, I'll come to apply. I'll come to structural and displacement. And in order to, I'm going to apply the boundary condition at this location, this location, this location, and this location, which corresponds to the key points in all these places. So in order to apply it in key points, but the visualization is in elements. So I have to change this visual to key points. In order to do that, go for plots, click on key points and key points. You can see here key points, but the numbering is not there as before. So in order to switch on the numbers, go for plot controls, numbering, click on key point numbers, and okay, you can find your numbers present here. So the first thing I have to do is that in the key point number 1, I have to apply a fixed boundary condition. So displacement on key points, select this first key point which is present here and click on OK, all DYF, which means the 3 rotation U of X, U of Y, U of Z, and the 3 translation and the 3 rotations are getting arrested by clicking on this all DYF and giving this displacement value as 0, which means it is a fixed boundary condition. So I can find a symbol here which corresponds to fixed boundary condition. And then the second is that I have to apply axial positive load of 5 kilonewton. So as the unit system that I am going to follow is in Newton, because in Young's modulus, while defining Young's modulus, I have given the unit of Newton per mm squared. So here I have to apply it in Newton, which corresponds to plus positive 5000 newtons at key point number 2. So I'll close this displacement, I'll open this force or moment on key points, I'll select the second key point, I'll click on OK. So it is default, it is in f of x, but you can apply in y, z, x, m, y, m, z, depending on your problem. Here I have drawn it in x-axis, so I'll use f of x, and I'll use a positive value of 5000 because it is right hand side, so it is a positive 5000. I'll click on OK, you can find the arrow mark. Then the third boundary condition is at key point number 4, which is 10 kilonewton, which means 10,000 newton. So it is at boundary condition 4. Again on key points, I'll click on 4, I'll click on OK, and I have to change this 5000 to 10,000, and I have to click on OK. So the second third boundary condition of 10 kilonewton is applied, and the final boundary condition 15 kilonewton at the very end at the 7th key point has to be applied. So click on key points, go for 7, OK, and change this 10,000 to 15,000 newtons in positive direction. Click on OK. So this is where your work is getting completed. So pre-processing stage gets completed here. After pre-processing, it is very much simple that you have to just solve by clicking a single button. Computer does all the work for you. So click on solve, click on current LS, which is current load step, and it will ask for a dialog box, and click on OK. So you can find within seconds, even within milliseconds, the computer has solved your problem. Right? So this is the power of computation that we have. So finite element analysis, where if you do the same problem with 300 elements manually, you are going to solve a 300 cross 300 matrix. So it is 301 cross 301 matrix. Reason being that if you have 300 elements, you will have 301 nodes. So one node greater than the element. So you are going to solve a 301 cross 301 matrix. Imagine how hard it would be while doing hand, but ANSYS solves it within seconds. So after solution is being done, then you have to view the results. So now what are the results that I am interested in this problem? So the main aim of this problem is that I am going to find the overall deflection of this problem. Then I have to find the individual stresses present in each and every cross section. So that we are going to take a look. So general post processor, there are lots of options, but the one I'm going to use is plot results. I'll click on deform shape, I'll click on deform plus undeformed, I'll click on OK. So you can find a colored variation here. This dotted line represents the actual beam and this blue color line represents the expanded beam, and here you can find the value without any units. As I said, APDL will not have any unit system in them. You have to keep it in your mind. So 0.09427 is the unit is mm, because I have already given all the units in mm. It is the overall deflection of this beam. And the thing that I always say is that don't trust FEA results blindly. Check your FEA results either with some experimental calculation or with some analytical calculation. So I have already done the analytical calculation for this problem here. So analytical calculation for the stepped bar. So deflection for a stepped bar is given by the equation PL by E, and the stress is load by area P by A. So which I have already done here. So the stepped bar, the overall deflection del L can be calculated by the sum of individual deflections of all these sections. So 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 7. So all these individual deflections, if you add it together, you'll get the overall deflection. I have done the calculations for you, right? You can go through this calculation part, right? PL by AE, that is typically the formula. So I have used, and I have found the results to be 0.094217. That is the analytical result. In ANSYS, what we got, you can find here 0.09427. This is the ANSYS result. This is the analytical result. If you find the percentage error, which is very much less than 1%, even very much less than 0.1%, 0.0725%, which shows that ANSYS result is very much closer to the analytical value what we got. Similarly, we'll now look at the stresses. And before going into the stresses, we can find this deformation value in a colored manner. So the main advantage of using ANSYS is that you can view your results in a colorful way. So go for contour plots, click on nodal solutions, and click on DOF solution, click on displacement vector sum, and click on OK. So you can find the colored plot of your deformation with the same value, 0.09427 being the maximum deformation, which is at the rightmost end. So you can save this image for your further reference. In order to do that, go for plot control, click on write meta file, invert white or black. See, as the ANSYS screen, you have a black color, and if you save the same image as it is, and if you are going to take a report or you are going to take a printout, and it looks a little bit odd. So I have to change this background black color to white color. In order to do that, go for plot control, click write meta file, and click invert white or black. So a dialog box opens. I'll change it to your desired location and give a file name. So I'll give it as deformation. So DEF, and click on save. So the file has been saved. You can find it here. If you minimize, you can find DEF. It is a .emf file. It will be opening in Paint. Actually, okay, it is asking for Paint. I'll always use this, and click on OK. Yeah, here you can find the values, but without the black color. You can find this white color, which is very much useful for preparing reports or taking printout. You can now save this using file, save as, and you can save in any image format that you wish. So I'll close this for now. Now we'll take a look at the stress. The stress cannot be directly seen as it is. Here you can go for contour plot, nodal solution, and instead of DOF, if you click on stress and if you go for one is a stress, and if you click on OK, you will find nothing here, nothing coming. You can find just a red color, completely red color, and no individual stresses have been developed. That is because while solving a one-dimensional structure, ANSYS does not show a direct stress result like this. For that, you have to do a little bit of a small coding thing that you have to do. In order to do that, go for element table, click on define table, and click on add, and now come here. Now I'll give this user label item as stress, right? And this, I'll come over here, and you can find the last. You have a by sequence number. Once you click that, here you can find a lot of codings here. I'll tell you what it is, but as for us now, just follow the procedure what I'm telling you. So default it will be SMISC, and here you can find that SMISC. Click on 31 and click on OK, and then again click on add. Go for by sequence numbering, SMISE and click on 36. So what does this number corresponds? What is this 31? What is this 36? And how to find this number? Is it unique? I'll tell you that in a bit of a moment, right? Okay. So for now, I'll just delete this. I'll again add it. I'll give the user label item as stress 2, and now I'll by sequence numbering I'll add SMISE 36. So this is not necessary that a user label item has to be given for each and every case. You can also delete this and you can just add it as it is. Okay, that doesn't mean anything. I'll also, so that I'll just leave that for your convenience, I'll just leave this user item as blank. I'll just click on this user by sequence numbering. I'll click on SMISE. I'll click on 36. It is just for your reference. If you are very much comfortable with this, just click on this 31 and 36. Keep this in mind. I'll tell you where to find this in a moment. Okay, and click on close. Now come back to this plot results. Come back to this contour plot, and at the end of contour plot you'll find line element RES. RES means results, line element results. I'm using a line element, so I'll click on this, and in this first one, element table item at node I, it should be SMISE 31. The element table item at node J, it should be SMISE 36, and the scale factor and all the other thing be default, and click on OK. Now we can find the stress plot, and the stresses are varying at each and individual section. A colored plot of this can be found. You can see a colored plot here. I'll just zoom over here. So you can find a colored plot for the first section, a colored plot for the second section, and another colored plot results for the third section. So in order to fit the view, you can use this fit view. Then another colored plot section. So in the last region, you can find an increasingly varying stress for each and every step, as it is because of a tapered section. The area keeps on changing. As you know that stress is load divided by area. As the area keeps on decreasing, the stress keeps on increasing, right? So you can find a variation of stress, a parabolic variation of stress in the last section, and you can find the maximum stress at this end, right? Now I have to, how do I know these individual values? By seeing this color plot, I can't get the exact results with this color coding that I find at the bottom. I need to know the exact values of all these individual section stresses. So you can also save this same image here. You can go for plot control. You can write meta file. You may save not meta black and save this image. But I need to know the individual values for all these sections. In order to know the individual values, so in here you can find only the minimum and maximum value, not the intermediate values. So I need to know the individual values for each and every section. In order to do that, go for list results and go for element table data. Go for this element table data. Click on this SMISE 31 and 36 together and click on OK. So you can find a series of results coming by. So you can find a series of same values. So this is the element number and the corresponding value. So we have divided each line into 50 segments. So we have almost 1, 2, 3, 4, 5, 6 lines. We have divided each and every line into 50 segments. So this first 50 segments will have the same stress value. Then this second 50 segment will have a same stress value. This third 50 elements will have the same stress value. The fourth 50 elements will have the same segment value. Similarly, it goes on like this. And this last segment, the stress value keeps on changing at a parabolic rate. As you can find the continuous decrease in area, the stress keeps on increasing. But in all the other section, you can find a constant stress values. So for that, so you can find from 1 to 50, you will have a constant value of 41 point. Exactly up to 50, you will have a same value. From 51, the section changes and the value changes. So from 51 to 100, you can find the same value here. So till 100, you will find the same value. After 100, again the section and material property changes. So you can find the next value. Again, it is constant till 150. And at 150, from 151, you can find the other value because the section and material property changes. And till 200, it is constant. From 201, it again changes till it goes till 250. And from 251, you can find a variation in stress, a continuous variation in stress. That is due to the continuous variation of the cross section. The taper section is getting continuously varying, so you can find a continuous variation of stress, and the maximum stress you can find at the 300th element of 45.014. Now I can't compare all the for all the other sections. I can compare the value easily. But for the taper section, I can't find the sections at each and every element. So I'll check this 250 first element, and then I will check with the 300th element. So these are the two values which I would be able to compare. But all the other values, in between values for this taper section, it is hard for to compare with the analytical solution. So the analytical results I have already compared for you. So the stresses you can find here. So section 1, 2, 2, 3, 3, 4, 4, 4, 4, 5, 5, 6 and 6, 7, the corresponding analytical values and the ANSYS values and the percentage error. In all these cases, you can find the percentage error to be less than even 0.1 percentage, which shows that there is a very much closer acceptance of ANSYS value with the analytical value. And for this 5 and 6 section, it is closer, and for 6 and 7, which is my tapered region, I have calculated the stress only at this end of 20 mm diameter. The in between value, it is hard for me to calculate and compare with analytical. Of course, you can calculate, but it is a little bit of work that you have to do. So I have not indulged in that kind of works. I have calculated for the 6th and 7th section, the cross section that I have taken is this at this end, this 20 mm diameter, which I have compared with that of the ANSYS values. So this is how ANSYS can be used to solve a stepped bar problem. So I hope I have cleared all your doubts or all your procedure in solving a stepped bar problem. I hope you find it useful. If there is any doubt at any stage, kindly contact me, so I'll be able to clear your doubts. So one more thing before closing this, I have to say is that, so I have solved this problem, but say I have to change a particular value. I have to add a particular new load at a location, fifth location. I have to add another one load. So I'll change this to key points. So I have added loads. The existing loads are at 2, 4, and 7. Consider that there is another load at this 6th node. So what I have to do, then go for preprocessor, click on loads, add another load at the 6th location, but don't forget to solve it again. Only if you solve it again, the values will get updated in your results, or else you will get the same results again and again, right? This is one thing. The other thing is that, suppose if I have given the value at load 2, so say the load at the key point 2, instead of giving it as 5 kilonewton as given in the problem, I have given it as 15 kilonewton unknowingly. There is an error has occurred. So what I have to do, I have to delete that load, then I have to reapply the load at that section. So I can go for apply. Instead of apply, you can delete the load, delete. So the same way that you have applied the load, you can delete the load. Delete structural force on key point, select this key point, and if you click on OK, the load will get deleted. But instead of doing this, so once the load is deleted, then again you have to apply the load, and again you have to solve this. This takes a little bit of time, but instead of doing this, there's a simple way for adjusting the existing parameters that you have already given while doing the previous analysis. So as I already told you, Mechanical APDL is one of the oldest ANSYS softwares that have been created really back. It dates back to 1990s, and while they were creating this ANSYS, they were doing lots and lots of coding actually. So ANSYS APDL means it is an ANSYS parametric design language, similar to that of a C program or a Fortran or C++. It is this ANSYS APDL has its own peculiar coding system. So whatever that we have done till now by clicking, it can also be done with the help of a coding, which you can find under the heading of session editor. So ANSYS codes all the thing that you have done till now as you have clicked. So you can find this requires a little bit of higher understanding of this software, but as for now, you can find something useful here. See, I have applied this beam188 is the element that I have added. Here you can find the Young's modulus 207.369 E3.33. So by looking at these values that you have given, you will be able to identify what is going on here. Here the metal property is being added. So similarly, you will be able to find. So what if I have to change a particular value? So here you have added the cross sections. Here you have created the key points. Here you have created the lines LSTR, which means linear straight line. So as you come down, you can find some load value being applied. Here you can find, so LE size, the element size is given as 50. Now if you want to solve with the higher number of elements, say if I want to solve the same problem with 60 number of elements, just change this 50 to 60 and click on OK. the entire problem will be solved again. Whatever you did from the start, it will do it automatically and it will give you an updated result. So now I will see, I'll go on plot control, deform the shape, deform plus undeform, and click on OK. So first we can find that it was 0.09427. Now an additional 2 has been added because the number of elements is increased. In similar way, you can change whatever that you have already given. So if this material property is wrong, you can rechange this material property, and if you click on OK, the ANSYS will do the entire calculation again and it will give you the updated results within seconds, so that you don't need to get to the preprocessor, edit it, again solve it, again come to the results and see it. Instead of doing that, you can just change the session editor. The only thing that you have to be careful is that you should not delete any unwanted commas. Even if you delete this single comma, it may result in some error that will creep into the software, because this is a pure coding. You should not tamper any codes that are already being developed by this ANSYS. That is the only thing. And the best way to save an ANSYS file is that by saving this session editor. Copy all the data in the session editor using Control A, then copy this, go to a notepad file. I'll open a notepad file and you can paste this session editor file, and you can save this in the form of a notepad.txt document. So at this desktop, I will save it as bar and I'll click on OK. So whenever you want to rerun this, just copy this, put it in this session editor panel or window and click on OK. The whatever you have done, it will be again be resolved and you will get your results. So this is one best way to save an ANSYS file. And one more thing I would like to add in this problem is that I have neglected the effect of self weight. So if you want to add that too, go for loads. So in apply, right? So you can find under structural, instead of force or pressure, you'll have find an option called as inertia. In that you'll find an option called as gravity. You'll find it under global. So there are three components: X component, Y component, Z component. So usually the gravitational force is in vertically downward direction, but that is in real world. This is an ANSYS software. Here it doesn't mean only the downward direction defines gravity. Here the default, there is no gravity. You can find all zeros. So even you can apply the gravity in X direction. Even if you want, you can apply the gravity in positive Y direction, or even if you want, you can apply the gravity in Z direction. So these are the things that you can do, because there is no defined gravity within this ANSYS system. So now I have modeled the problem in positive X direction. I'll give my gravity in positive X direction. So please be careful while giving it. Don't give it as 9.81, because the unit system will get wrong, because previously we have used mm as our unit system for length. Here 9.81 corresponds to meter per second squared. So I have to change that to mm per second squared in order to cope up with our problem. So it should be 9810 mm per second squared. And if we click on OK, now as I have done some changes to preprocessor, I have to solve it again in order to get my updated results. So click on solve, OK. So you can find solution is done. Now if you see the results, there will be a change in value. So I'll just deform plus undeform, I'll click on OK. Here you can find many change actually, because the effect of gravity is very much smaller here, and it does not produce any considerable deformation, maybe that is why. But in some cases, when you have a very large structure, the effect of gravity will be very much huge, and you will get some changes in this value. But in our case, we didn't get any change in values. But this is how you apply the inertial gravity here. So similar way, you can also apply pressure or temperature, and it corresponds to some specific problem. As far as our structural problem, you don't need to apply any pressure or temperature here. So this is one additional data. Also, if I have to, this is, as I already told you, we have modeled the problem as one-dimensional problem. But if you want to take a look at it such that how it looks in 3D, if you want to see our problem that how it looks in 3D, you can do it. Do one thing. So plot elements. Now go to plot control, click on style, click on size and shape. Instead of here the display of element is off, so click it as on, and if you click it as OK, you can now find this is 3D. Now I will change the view to oblique or isometric, and here you can find the three-dimensional view. This is just a representative form. We have not actually modeled the problem in 3D. We have modeled the problem only in 1D, but this is a visual representation of how it will look in 3D. So just a visual representation, that's all. Okay, now even if you want to see the results in 3D, you can do so. So click on DOF solution, displacement vector. Okay, so you can see the displacement vector in colored plot in 3-dimensional way. Okay, you can also save this image as you want. So click on write meta file, invert beta flag, do whatever you want with the help of this menu. So this is all about solving a stepped bar in ANSYS. So I think I have incorporated all the complications in a single problem. Right now, it is your time to solve your individual problems. Now try to understand each and every step slowly. Pause the video, understand the step, and after understanding the steps, try the problem in your own way. Try to do the same problem what I taught you here. Then you can go for solving your individual problems. So thank you so much. So I'll sign off now. We'll see in another video for our second exercise. Thank you so much.